All right, Vanya, we're going to get started, I guess. So, Vanya, live from Zagreb to talk about non-local quadratic forms. Please, the floor is yours. Take it away.
Okay, thank you. So I would like to thank the organizers, Anahan, Avi, and Pavan, for organizing this young researchers or junior researchers seminar within our programs. My program has already finished a month ago, so I'm happy to be able to kind of connect to the institute, at least remotely. So today, the goal of my talk is basically to introduce a new notion of non-local processes which correspond to the classical non-local, for example, alpha stable process on a domain which exhibits certain diffusive behavior. So we will talk about the type of diffusive behavior that we are interested in, and we are going to introduce these type of processes, starting with their Dirichlet forms, and then we are going to investigate precisely how much do they correspond to this diffusive behavior that we are looking at or looking for. So the goal of today's talk is the following. We are in general going to look at non-convex open sets. So D will be a non-convex open set. And the idea will be in step one to introduce the so-called visibility constraint process through its bilinear form. So we are going to define a Dirichlet form. I will say what the Dirichlet form is, define it, and connect it with the process, and try to explain why we use the theory of Dirichlet forms in this setting to somehow introduce the process in the first place. So we are going to define the Dirichlet form with the so-called visibility constraint. So this visibility constraint will basically mean that the process can jump from one point X in D only to those points in D which are visible from the point X. Then in step two, we are going to investigate the regularity of the defined Dirichlet form. This will be important because this regularity will give rise to a certain stochastic process. And we will call this stochastic process precisely the pure jump process with visibility constraint. And then in step three, we are going to investigate the corresponding Poincar constants or the optimal Poincar constants in the Poincar inequality exhibited by this visibility constraint Dirichlet form. And this sharp Poincar constant will precisely give us this connection to the diffusive behavior we are looking at. So we are going to investigate the let's call it diffusive behavior through the Poincar inequality. Inequality. Okay, so this will be my goal for today, and to somehow start with the first notion, the definition of the visibility constraint Dirichlet form, I want to give some motivation. So if we have a class, I know this is very far off from most of the work within the free programs within this seminar, but my goal for this talk is to somehow introduce you to a new type of pure jump process which has some physical properties which are more alike to diffusive behavior than the pure jump behavior. And when we talk about this diffusive behavior, we precisely mean the pathwise behavior of the process within a certain connected domain where a diffusion has to somehow crawl through the domain in order to pass from one part of the domain to the other. So basically, if we start with a union of two disjoint open sets, so let this be D plus and this D minus. If we have a diffusion on this union D, this diffusion can basically be split up into two diffusions, depending on if we start a diffusion in D plus. If we start a diffusion in D plus, then this diffusion can't pass, if we just restrict it to this set, it cannot pass outside of D plus. So it will be just the diffusion inside the set D plus. And also, if we start a diffusion in D minus, then we basically get some diffusive behavior in D minus. So in order to examine a diffusion on the whole set D, we basically just have to examine it on D plus or D minus, depending on where we started. But if we have a pure jump process, what can happen? So if we start in D plus, our process can jump in D plus, and then from D plus jump to D minus, and then from D minus to D plus, and then back and forth. So this this lack of connectedness does not pose any type of barrier for the jump process to interchange between the two sets. Okay, so what happens if we connect these two domains with some small corridor? So just take some corridor gamma here. Okay, now the diffusion can pass from one part of the domain to the other, but this has to happen precisely through this corridor gamma. So this is the only way you can pass from D plus to D minus. If we have a jump process, then the jump process can, of course, pass through the corridor, but it can also pass directly from D plus to D minus. So we can do this jump directly or go with several jumps through the corridor, depending on the properties of this pure jump process. So what we want to examine, or what we want to define, is diffuse is a pure jump process, such that the only way this process can pass from D plus to D minus is by passing through the corridor. So in some sense, we want to define pure jump processes on subsets of the domain, so on D, such that the passage from one part of the domain to the other has to go through this corridor. So has to be, there is no pure jump between D plus and D minus. Okay, and this intuition, somehow this motivation, came from a group of physicists who were actually discussing some diffuse behavior in these dumbbell-shaped domains. So this is a dumbbell-shaped domain. In some sense, you have this corridor connecting these two, let's say, like balls or some bigger domains. And the idea was, so we want the physical particles, when they move, they really do not, if they move within a dumbbell-shaped domain, they really, even if they jump, they don't move by jumping from D plus to D minus. They somehow have to move through the corridor, at least in some settings that they were looking at. So they were interested in this type of pure jump processes, but in some sense, there is some jump component in this physical movement. So they want to model it using jumps, but they want to see this diffusive behavior by passing through the corridor. And this was basically the motivation for the introduction of these visibility constraint processes. So in what is basically the idea that we decided to go with? So the idea is the following. We are going, so let's take this annulus D, and we are going to define a pure jump process that can jump from a point X in D only to the points which are visible to the process within D. So basically from the point X, you can only see this area. So the jump from point X is allowed only within this area, which we will denote by dx. Okay, so this is one way to define, let's say, a process that will exhibit some type of diffusive behavior, which we will see later. Another way to do it, and this is also a very important setting because we use it heavily within the visibility constraint research. This is defining the jumps or allowing only the jumps from point X to within a ball. So within a ball with the radius up to the distance to the boundary. So the largest ball contained in D, centered at X. Okay, so one can also say, let us only allow jumps within this ball Bx. Okay, so these are two types of jump restrictions that will allow us to define the jump process of this type that has to pass through the corridor within the dumbbell-shaped domain. And of course, if we have a very weird non-convex domain, it is very hard to somehow look at specific visible parts from each point, because this depends heavily on the type of the domain you are looking at. So this is heavily dependent on the form of the domain. So what we usually do, we just look at we can somehow jumps within this set dx. We can somehow, at least from below, dominate, or below, we can bound from below by these jumps within the ball Bx, so the largest ball contained in D centered at point X. So somehow the analysis for this visibility constraint process that I will be talking about today boils down to the analysis for this process that can only jump within the ball, the largest ball contained in D around a certain point. So just to keep in mind, these are two different processes that arise, but one can show that they are heavily related, and I will talk a bit about this also later on. So in general, the idea is to look at non-convex domains. Why non-convex? Because if you take a convex domain, then you are allowing jumps from each point to each point in the set D. So if D is convex, then dx is just D. And these type of processes for which you allow jumps within the whole set, these type of processes have already been very well studied. They are called censored processes, and they were a part of my talk within the fractional differential equations seminar. So anyone interested in these type of regional processes can also take a look at the seminar I gave in April. I will also talk a bit about them later on, because this is also important for the definition of the non-local visibility constraint process. Okay, so to start with, let me talk about the regional Dirichlet forms. So what is a Dirichlet form? I guess many of you maybe are not well versed in this analytical tool. So this is nothing else but a bilinear form defined on the product f times f, giving values to R, where f is basically a dense function space in L2X. X is some measure space. X mu is some measure space. And here we said f needs to be dense. This is a bilinear form, meaning that it is symmetric. Then this means that EUV is equal to EVU. It is non-negative, meaning that EUU is non-negative for all functions u in f, then f needs to be closed with respect to the product we call E alpha. This is nothing else but the bilinear form evaluated at two functions plus some constant, positive constant alpha times the L2 product of u and v. Okay, and we need E to act on the normal contractions. What does this mean? This means that if we define function u tilde to be the cutoff function, so you take u and cut it below 1 and above 0, or cut it below 0 and above 1, then E of u tilde is less or equal than EUU. Okay, so now having this Dirichlet form, we can analyze behaviors of various well-known processes. These are usually Levy processes, Levy-type processes, and Feller processes. I will not talk directly of the correspondence between these two, but it is very well studied and known that all nice Levy or Feller processes have a corresponding Dirichlet form, and you can somehow discuss the pathwise behavior of your process by looking into the analytical properties of the Dirichlet form. The thing also goes to the other, so we can also go in the other direction. So moving from a special type of Dirichlet form, we can find a unique, in the sense of distribution, nice strong Markov process corresponding to this Dirichlet form. We just need to pose this additional property of regularity. So we say that EF is regular if it possesses a core. So what is a core? Possesses a core. So this is a subspace of function C contained in F, and these need to be continuous functions with compacts in support on X, such that C is dense in F with respect to this norm defined through E alpha that we have here, and C is also dense in CCX with respect to the uniform norm. Okay, so this is some property of a really nice in the sense that you have denseness in the space of continuous functions with compact support, functions which are also, with which you can also approximate all functions in F. So we need this very nice approximation function space. And if we have a regular Dirichlet form, then it is a very old, very well-known result by Fukushima from the 70s, which says that every regular Dirichlet form corresponds to a unique, symmetric, strong Markov process. We get a bit more than a strong Markov property, but for now it is enough. Strong Markov process on X. So starting from a regular Dirichlet form, we know that there exists a strong Markov process corresponding to this Dirichlet form. And by studying this Dirichlet form, we can say something more about its pathwise behavior. Okay, so first, maybe I shall add another page here. First, let me say a bit about bilinear forms without visibility constraint. So let me define what I will call the censored process on D. D is here open. Okay, so basically we can take any type of Levy type kernel. So this is a kernel from D times D, it doesn't have to be defined on the diagonal, because we can allow for explosion rates, or we can allow for singularities within the diagonal of the jumping kernel, which takes values in 0, infinity, which is a measurable symmetric function, measurable and symmetric. And we need this kernel to satisfy a certain type of Levy type integrability condition. This means that if we integrate over set D outside of point X from any point X, so we look at the jumps from any point X in D, then this kernel basically needs to integrate. This kernel has to have a finite integral of large jumps and has to have the finite second moment of small jumps, which means that this integrates 1 minimum x minus y squared dy. And not only do we want this to be finite, we need the supremum over all x in D to be finite. So this is some type of Levy type integrability condition on the kernel. Once we have this integrability condition, what we can define the following bilinear form, EUU, as the double integral over d times d of u of y minus u of x squared kxy dy dx. And with this definition, and by taking the domain F to be the closure of CC infinity functions on the set D with respect to this inner product E1, recall E alpha was the inner product that we defined on the previous page, and all of these inner products are comparable for different alphas, so we can always just take alpha to be equal to 1. So if we take E, if we define E in the following way and take the domain F in this way, what we basically get is a Dirichlet form. EF is a Dirichlet form on L2D. And this Dirichlet form is a regular Dirichlet form. It is regular on what I will write down as L2D bar. Of course, defining an L2 space on a set or a closure of this set doesn't make much sense. What is important when I write it like this is the core of this regular Dirichlet form, meaning that the core for this this process is basically the continuous functions with compact support on the closure of the set D. So this is the core. Okay. And now Fukushima's result gives rise to a symmetric Markov process Y corresponding to EF. And I will call this process the sensor process on D. And this is a process that lives on the closure of the set D. So if we want to talk about this process, we basically want to talk about its pathwise behavior. And talking about the Dirichlet form doesn't give us any notion of how this process behaves actually. So what one can show is that the process corresponding to EF, so Y can be constructed through the so-called Ikeda-Nagasawa-Watanabe piecing together procedure. Ikeda-Nagasawa Watanabe piecing together procedure. So what does this procedure say? I start from any point X in D, and then I start my process as a regular process with jumps given for this kernel KXY. You can think about this kernel KXY through a model example. So some constant over x minus y to the power d plus alpha, where alpha is in 0, 2. This is the jumping kernel corresponding to the so-called alpha stable Levy process. And this is the model example of pure jump process that usually arises so when you move straight from the Brownian motion to some non-local setting. I hope everyone is at least a little familiar with this. So what do? By following this kernel, you start the process from any point x in D, and now it jumps anywhere. At the first time where it jumps outside of set D, you ignore this jump. And what you do, you move to the limiting position before the jump. And here you restart a new copy of the process. So here you restart another copy independent of the previous one. And when the process first exits the set D now for the second time, you again ignore the jump, you move back to the limiting position before the jump, and you restart a new copy. And one can show that you can do this infinitely or countably many times, and two types of behaviors can happen. Either your process lives infinitely long within the set D, or it can somehow approach the boundary and die out at the boundary in finite time. So there are two types of behaviors for these processes, and you can describe which type of the behavior you can expect, or which type of we call this conservative behavior arises depending on the boundary of the set D. So the boundary, the type of the boundary and the type of the kernel give rise or can immediately tell you, will the process live infinitely long almost surely, or will it almost surely die out? This is for bounded open domains. Okay, so now we don't want to look at the whole process. We just want to look at the process with visibility constraint jumps. So what is the idea? Instead of defining the bilinear form in the way we did, so this was the bilinear form with kernel K, we will now allow only those jumps from point X which are within the visible area from the point X. And we will call this bilinear form eVis, like visibility. And again, we define the domain for this bilinear form to be the closure of CC infinity functions on D with respect to the norm defined for this inner product, eVis1. So why do we use this space? Usually because for CC infinity D functions, these forms are finite. This is due to this integrability condition on the kernel K that we noted. And now we can just take the closure. We can define EUU for all functions for which we have this approximation via CC infinity D functions. Okay, so these type of definitions. So this is a regular Dirichlet form, and it's again, because this is a bilinear form, maybe you don't see immediately that it is symmetric, but it is. Why? Because we can write down, in essence, it boils down to the fact that y is visible from point X if and only if X is visible from point Y. But this is precisely 1/2 double integral over D times D, U of X minus U of Y squared kxy 1 dx y plus 1 dyx. So here you see the symmetry, that this is truly symmetric bilinear form. And the parts that I didn't comment on, the closedness and the normal contraction, follow directly basically from the type of this kernel K from this integrability condition. So this is not an issue. Okay, the idea is now the following. We we know a bit about maybe the regularity of this. So we know that there is a process corresponding to this form. E vis F vis is a regular Dirichlet form. So we know that there exists a process, a symmetric Hunt or strong Markov process X corresponding to it. And this jumping kernel here basically tells you the pathwise behavior. You can do the same type of piecing together procedure that we saw on the previous page for the full process without a visibility constraint. But what we want to actually look into is not only this process, we also want to look into the following process, or we want to discuss the existence of the following process, the process corresponding to what we call this Dirichlet form, where F vis bar is the space of all L2D functions such that the visibility form is finite on this function. So note that this is in general a larger space than F vis here. And we want to talk about the regularity now of this new Dirichlet form and the existence of the corresponding process. So the regularity of these forms usually has its own not only through the existence of process, but it has its own mathematical value, because much like in this setting, in the last one where we saw the definition of the censored process, one can pose the same question. So one can say, okay, given a certain integrable kernel in this Levy integrable kernel, what can we say about the regularity of the form E F bar, where now F bar is the space of all functions for which this bilinear form is finite. If you take this kernel to be the alpha stable kernel, then this space F is nothing else but the closure of H alpha half space, or the closure of CC infinity functions on D within the fractional Sobolev norm, and F bar is precisely the H alpha half space, so the fractional Sobolev space. And the idea is, of course, to talk about the regularity of this space, or when are these two spaces the same, F and F bar, and when these two spaces differ. So it is much the same type of question. Okay, so we want to be, our question here is, can we say something about the regularity of this form? And when are these two domains the same? Why? Because if we have that these two domains are the same, then the corresponding process here for this regular form is precisely the process that lives only on the set D. If it lives only on the set D and not on D bar, then we can maybe say something about this long-term behavior of the process that I mentioned. Does the process die out at the boundary, or does it live longer? In any case, all of these questions can be answered through the comparability of bilinear forms. So these are some motivations for why would someone want to look into the comparability of our original bilinear form E and the visibility constraint bilinear form. So this comparability will basically give us a way to discuss pathwise property of the visibility constraint process by just looking into the property of the censor process. And since the censor process is very well studied and we know the pathwise behavior of these type of regional processes, we can immediately say something also about the visibility constraint process as well. So these comparisons the results are very important in this line of investigation, but also as a question, as an analytical question in itself. So what we basically examine is, as the main tool, is the comparability of these two forms. And one can show that under certain conditions on the kernel, where we ask that the kernel has some type of, let's say, scaling behavior. This is some type of fractional behavior. So we only look into kernels which are of the following form. The kernels are of the form L, some function L of the distance of the 2 points over x minus y to the power d, where L satisfies a certain scaling condition. So this scaling condition is of the following form: L of lambda r over L of r is dominated above by some constant times lambda to the power minus delta, and from below by some constant times lambda to the power minus gamma, where these constants are independent of the choice of lambda and r. This inequality needs to hold for r small and for all lambda greater or equal 1. Okay, and these constants gamma and delta, gamma is greater or equal than delta, are between 0 and 2, strictly between 0 and 2. What does this mean? This basically means that this kernel kxy is bounded from below and above by two fractional kernels. I will call this alpha 1, and this will be d plus alpha 2, because alpha 1 and alpha 2 are basically delta and gamma, depending only on the fact are x and y close or x and y far apart. But in some sense, you allow for jumps which are not only alpha stable, strictly alpha stable, okay, but they are not strictly alpha stable, but they are somehow comparable to a combination of stable processes. Let's call it like that. Okay, so if we restrict ourselves to these type of kernels, and if we restrict ourselves to bounded uniform domains D, bounded uniform domains, I will show you a picture to explain what this means, then we have the comparability result between these two bilinear forms. And these are results that have been studied for some time now. First by work of Bartek Bida, then later on work by Prats and Kassmann, and also some very recent work by Artur Rutkowski from Wrocław. Okay, so let me say a bit about these uniform domains. I think it's best to show it in a picture. So one very nice example of a bounded uniform domain with very rough boundary is the Koch snowflake. So Koch snowflake is an example of a uniform domain. This uniformity means that any two, so you can divide your domain in these type of cubes, okay, and you can connect any two cubes. Maybe you can see it here and here. These are two red ones. Via an admissible chain of cubes. This means that you can travel from one red cube to the other by connected cubes, such that the size of the cubes progressively enlarges and then progressively decreases. So you need to have some comparability of these neighboring cubes when you travel from one point to another. And respectively of the position of any of these cubes, you can always connect them with such finite chains. This uniformity of these domains allows us to do this connection of jumps by saying, okay, my jump from one red point to the other red point, which is allowed by the full bilinear form E, can be somehow, let's say, explained through the following jumps: from the red cube to the next green one, and then to the next green one, until we arrive to the centered blue one, and then we move back with these progressive jumps. And these progressive jumps through the visible areas, note that you can always choose these cubes such that the neighboring cubes are visible from one to another, and then you can always move through the visible area from one point to another with these, let's call it progressively enlarging and then decreasing jumps, which then give you somehow the path, which is comparable to this one jump from one cube to another. And then we get the comparability. So this is just some idea of the proof, or some idea of this notion of comparability. Okay. One domain, which is specifically not a uniform domain and which is very hard to tackle. So anything with cusps. So if you take anything with cusps, this makes things quite difficult. Or for example, if you have like a swirl, infinite swirl, which is decreasing. So you have infinite swirls, which are decreasing. These are non-uniform domains, and this is the setting that we cannot tackle. But for example, anything relatively nice, even with rough boundaries such as Koch domains, can be so here we still have comparability due to this uniformity of the domain. Okay. So now that I've said something a bit about the comparability, this is also a very important property for studying the diffusive behavior. I want to say a bit about the diffusive behavior of our new process, the visibility constraint process. So in order to study this diffusive behavior, we are going to look at the Poincar inequalities and the sharp Poincar constants in certain type of dumbbell shape, let's call it dumbbell shape, infinite dumbbell shaped domains. So we are going to look at the Poincar inequality. So first, let me show you the type of domains that we are interested in. So these will be the unbounded domains that we generally think about. So we have two convex, unbounded, very similar domains, D minus and D plus, which are note we need some linear progression of the size of the balls. So if you look at the part of the ball contained in D minus and D plus, this part of the ball has volume always of some constant times RD, okay, or is always between two constants times RD. And they are connected through some corridors. These corridors are usually very small, or are small in comparison to the unboundedness of these D minus and D plus. And you can have two types of connections. The first connection like this, you see that you can see through the corridor, meaning that our visibility constraint process, if it starts from D minus, can jump through the corridor to D plus without moving throughout the corridor, but jump straight directly through the corridor to D plus because there is visibility through the corridor. On the other hand, if you have such a corridor where there is no direct visibility, so the visibility constraint process has to first jump into the corridor and then from the corridor back to the D plus, or maybe jumps a few times through the corridor and then move to D plus. So here you really have movement throughout the corridor. So depending on this visibility within. So this will be one type and this will be the other type of the domains we are looking at. So what does the Poincar inequality look for a diffusion? Let's just take Brownian motion in these type of domains. So what I will denote by dr is only the part of this domain which is contained inside the ball of some very large radius r. Okay, so if I have a Brownian motion, then my Poincar inequality looks like this. So I take u of x minus, this is the average value of the function u within this set dr to some power p. This is less or equal than some constant independent of choice of u and radius r. So this is just some constant times r to the power d. And here we have precisely the bilinear form for the Brownian motion. So this is in LP. This is for P which are strictly less than the dimension of the space. And if we have P equal to the dimension of the space, then we don't have only RD here, but we have also an additional term. This is precisely log R to the power P minus 1. And here you have the same bilinear form. Okay, so you can think about this when P is 2 as the bilinear form for Brownian motion. This is precisely it. Okay, so here you see that this sharp constant is of the form r to the power d. But if we take the bilinear form E, so the left-hand side is the same. Then here we just get r to the power, here we will have p alpha half e uu. So we see a completely different sharp Poincaré constant if we take the full bilinear form E corresponding to the sensor process, where the jumps are allowed throughout the domain D. But if we look at the visibility constraint bilinear form or the visibility constraint process, so this will be for the censored. And if we take the visibility constraint, then on the left side, we still have this, and on the right-hand side, so we have less or equal than some constant times r to the power d e is uu. So this optimal Poincaré constant is precisely the optimal Poincaré constant that we see in the case of Brownian motion, the very specific diffusive behavior. And this holds for the domains where we do not have visibility through the corridor. No visibility through the corridor. So if you recall, let me just show it quickly once again, this means that we have this type of domain. If we allow some visibility through the corridor, as in the first setting, then we see that our process or our sharp Poincaré constant exhibits a very peculiar transformation for very specific types of kernels. So if we allow visibility through the corridor, then this constant here will not be r to the power d anymore. It will become r to the power d r to the power d minus 1, L of r to the power minus 1, whenever L of r is greater than 1 over r. So maybe you do not recall well what this L was, so let me write it up in terms for the fractional setting or the alpha stable process. Then this constant r to the power d now changes to r to the power d plus alpha p over 2 minus 1. Oh, sorry, this is an exponent. So let me just move it up. This is an exponent. As long as here we have, as long as alpha p over 2 is less than 1. So as long as we have small alpha. So for small alpha, we don't get the true diffusive behavior r to the power d, but as long as alpha is relatively large, then we get the same type of diffusive behavior even when we allow the visibility through the corridor. So this optimal Poincaré constant is related to the smallest eigenvalue of the corresponding operator or the generator of the process. So somehow through this, we see that there is this connection to the diffusive behavior, not only in the pathwise setting, but it is somehow reflected also through this, let's call it, progression of the smallest eigenvalue of the corresponding generator. And this was somehow our small analysis of a non-local process which exhibits these type of, let's call it, physical diffusive behaviors with this creeping through the corridor. And the Poincaré inequality gives us an analytical, let's call it, justification of this type of, let's say, analog. This is a work in progress because there are many open questions, and so far I have to admit there are no strict applications, but I hope that I was able to somehow relay this notion of pure jump processes that still exhibit some type of diffusiveness. So although your problem, your physical problem, might be in essence diffusive, you can still incorporate some jump representations if needed and still regain this physical diffusive behavior that you're looking into. So I hope this was some type of motivation for everyone doing explicitly diffusive settings to also take a deeper look in some possible super diffusive notions that might give rise to maybe some further physical properties that you haven't been looking into. So thank you so much. I hope I didn't take too much time, and if you have any questions, I am here.
Thank you, Vanja. Any questions here in the room or on Zoom? Avi, do you have a question?
Yeah, hi, can you hear me?
Yes, hi, Avi.
Hi, thanks, Vanja, super nice talk. This might be something that you said that I missed, but so in these estimates, you're talking about optimal Poincaré constants. How do you know they're optimal in a sense? Yeah.
Okay, so I have to say I was cheating a bit. They are mostly optimal. So how do you show that it is optimal? First, of course, you find an upper bound for all functions. So this is an upper bound for within the whole domain F. The way that you find this upper bound is using these progressive expansions of balls. So our domain looks like this. I know your question was more in lines of optimality, but let me just show you. This gives an idea also of how you choose your test function to show the optimality. So you start by saying, okay, I move from this ball, which is visible throughout the corridor. If I don't have visibility, then again, I just take two small balls which I cannot connect through a series of visible areas. I don't care. This is what I can do because my corridor is, let's say, uniform. And then I expand these balls progressively, somehow. So every jump from any point here to any point here, I can somehow do in the following setting: jump from here to here, from here to here, from here to here, through the corridor or throughout the corridor using these small jumps, and then from here to here to here to here, and then to here. So this is how I compare this one big jump that my sensor process can do with these small jumps that only the visibility process can do. And how do I then test that this is the optimal constant? Well, the usual suspect example is the following. I just take here to have 1, and here I have -1. So I take function, which is 1 here, -1, and I take some smoothness through the corridor. And I evaluate or find the lower bound for EUU of such a function, either EUU or EUU visible. Or the gradient, I don't, in any sense, you get either you integrate the gradient. So this is somehow the suspect function, because if you just look at the jumps from left to the right, if you recall the bilinear form, here I have u of x minus u of y. So if I just take the part from the left and part to the right, and I integrate jx minus y dy dx, here I get, oops, sorry. Oh, sorry, just a sec. Ah, do you see me again?
Yeah, I can see that.
Yeah, okay. So here in the ux minus uy squared, here you just get a 4, and then you just integrate the kernel with small jumps. So this is some constant. So you get just some constant, which is comparable to r to the power d.
I see.
So that's the basic idea. The problem is the following. That's why I said I wasn't too explicit, that this constant r to the power d here is when you have no visibility through the corridor. This is sharp for all type of kernels. But this constant here, so you have r to the power d for large alpha. You have r to the power d plus this correction term for smaller alpha, less than, for alpha p over 2 less than 1, and this is sharp. But if you have equal here, then the sharp constant here isn't r to the power d, which one would have because this is 0. It has some, we suspect that it has some logarithmic term.
Sure.
And and this is basically what we got by evaluating through this exemplary example, this -1, 1 function. The problem is to show that this is truly the upper bound. So getting the upper bound of this r to the power d, I guess this would be over log r or something like this. Has proven somehow trickier. And I suspect that some potential theoretical procedures might help, but so far we haven't been able to work this out.
Okay, nice, thank you.
Thank you so much.
Jen, do we have the time?
Oh, sorry, I think I see a question on the chat.
Yeah, if you want to take a second to reply to.
Let me just see. This is from Xiaochuan. Hi, Xiaochuan. Is your Poincar inequality somehow related to one on the Gaussian space? Variance bounded by square norm of the gradient. Yes, this is precisely that. So I don't know if you've seen the R Poincaré constant related to the one of the Gaussian space. Yes, so this is precisely this constant. I don't know if Xiaochuan is still here.
Yes.
Hi.
Hi, Vanja. So I was asking this because the left-hand side used the Lebesgue measure, and the usual Poincar inequality used the Gaussian measure. So I don't know if you can translate from one to another.
So I am not 100% sure that the answer is yes, but my conjecture is yes.
All right, good. Thanks. Nice talk.
Thank you.
I have a more general question. So I'm more of an engineer than a mathematician, so I don't understand the details, but I was just wondering what processes are better modeled as jumps and what processes better modeled as diffusion, and where would, if I've understood it right, Here, it's something in between, right? So what processes would this, so what sort of processes are being modeled using this? And I really liked your diagrams. Thank you so much for this.
Thank you. So I have to say that when this, so let me first start with the censored process. So this is the pure jump process on the set D that I described in the first part. So I have seen some explanations on the possible usage of these type of jump processes in modeling, let's say, movement of predators within a region. But I've also seen some refutals of these type of theories. So, you know, and we also had a huge discussion within our program. What are the precise applications of these type of processes? So I can only tell you what I saw in the literature. These are basically, you know, the papers you grab hold on to, and then you put them in your motivations and so on. But it is not very clear how truly applicable this is. But for example, if you have, so I don't know what would be the word for a group of sharks. They would feed in one area and then they would make like a big jump and then feed within another area and then make a huge jump to another feeding area and feed in small jumps here. So there were some let's say, there was some work in this area where they tried to use these jump processes within a domain for modeling these type of predator behaviors. The question, so the motivation that came from the physicists in this setting, especially from these dumbbell-shaped domains. So, for example, for the physical interpretation, the question was, it really, I mean, we basically have a particle. This is the boundary. So this is some very hard material. Our particle cannot go through the material from this part to this part. But since there is some, for example, if you have some type of porous media, then this, what this would be the diffusive behavior. Somehow, when it's measured, sometimes it looks more like jump process than a diffusion. When they look into the measurements, they somehow get this more of a jump idea of a jump process than a diffusion in itself. So modeling it that way would maybe make sense for them, but also you have to keep, so you want a jump process, but you also don't want to allow these jumps through the hard barrier. So this is why the motivation, the idea came, okay, do we have any type of example of a jump process, and that we know something about this process, such that you still have to pass through the corridor. It still has to somehow respect the limitations of the physical world. So you cannot jump through this hard barrier. But in terms of real explicit applications, I cannot tell you anything because at this point we are very, very far from anything very applicable. So this was just some, you know, it started as a small discussion, and but for me, I found it very interesting to maybe also keep in mind that you can get some diffusiveness, and you can still rely heavily. So what we do, we heavily rely on the characteristic of this process that can jump to any point within D in order to analyze this process that cannot jump through the barrier. So you still use heavily this pure jump process, the full pure jump process, to analyze this very specific jump process with certain diffusive behavior. This was just, let's say, a first step in this direction. I'm sorry, I didn't help you or answer you very much in this general area, but I hope that at least some type of possible intuition or for application that you can see it.
All right, well, let's thank Vanja again for the very nice talk and ensuing discussion. So thank you.
Thank you so much, and I hope to see you within these several last talks that we have in June.
Yeah, we have a next round of talks next week, so
good.
Go there. Thank you.
Bye-bye.